Today I'd like to trace the origins and the early evolution of large-scale production. Large-scale production was central to the Industrial Revolution in the United States. And at the heart of large-scale production was machine tools that worked metal. These machine tools, which became more specialized over time, were brought together in factories. And these factories contain new machines, new kinds of machines, power-driven machine tools, and also, equally as important, new ways to organize work, new ways to organize the machines, to control the machines, and also to organize and control the workers in the factory. Now, there were two related objectives in the use of power-driven machine tools. The first one was to speed up and cut down the cost of shaping and cutting metal. The reason for this, to try and shape and cut metal to whatever size, whatever parts were needed to make the final product. The flip side of this, as part of the reason for it, part of the cost reduction by doing it this way, was to reduce one of the most expensive parts of making a product, and that was hand finishing. Even if parts weren't made by hand, where all the work was done with hand tools and on hand and foot-driven machinery, a large part of the total labor cost of making fairly complicated products was hand finishing, grinding down pieces of metal, and then trying to fit the pieces of metal together into the final product. The ultimate goal of the evolution of the use of power-driven machinery in factories, the ultimate goal was to produce interchangeable parts. To produce parts that, first of all, every copy of the part was as close as possible to each other. We'll talk about why that was important. And also that every copy of the part would be as close as possible to a perfectly sized part, to an ideal part, a template, so that when it became time to fit the parts together to make the product, is that the parts could be fit together with a minimum amount of finishing, a minimum amount of filing, fitting them together. They don't fit, take them apart, take the part, you put it in a vise, you have a hand file, you have to file it down again, and keep doing that back and forth until the parts fit together. Then you take a third part and start the whole process all over again. Expensive, time-consuming. So that was the objective here. And why it was done for different reasons. We're going to start by taking a look at one of the first large-scale production industries in 19th century America, the production of clocks. There was a serious attempt to design machines that could produce interchangeable parts that would be brought together to be assembled to make clocks. The main reason for this was that to reduce the cost of producing the clocks. Now, clocks in 1800, in colonial America and then into 1800, clocks were very expensive. They really were a luxury product. The reason why they were a luxury product is because they were made by skilled craftsmen. The works were made by metal workers, and then the cases, the tall case clocks, the cases were made by cabinet workers. They were made with hand tools and hand machinery. It took a long time to make the clock works by hand. In fact, the records we have of maybe the most famous clockmaker in the late 1700s showed that on average he made 4 sets of clockworks per year. The clockworks themselves cost, without the case, the clockworks themselves cost about $50, which was more than most American families made in a year. So we're talking a very expensive product because of the tremendous amount of time and skill it took to make the parts, to put them together, to fit them together, to file them down, fit them together again so that, in fact, the clock could work. Clockworks traditionally were made out of brass, but brass in America in the late 1700s was very expensive, so that many clockmakers began to substitute wood, again, a relatively cheap material, for brass, even in the works of the clocks. By 1800, in fact, over half the clocks made in America had wooden gears, a wooden mechanism in the clocks rather than brass. Now, in 1802, a Connecticut clockmaker by the name of Eli Terry decided that there was a large latent demand in America for cheaper clocks. He saw the increased urbanization, the increased size of the commercial class. He felt there were a number of people, a number of groups in America that would buy clocks if they were cheaper. They just couldn't afford these very expensive handmade tall clocks, now called grandfather clocks. So what he decided to do was to try and bring the cost down of producing clocks. And at the heart of what he was trying to do was the use of water-driven machinery. Speed up the machinery, over time design new machinery, more specialized machinery that also become more efficient. And that's what he did. He built a plant with water-driven machines, and in fact he was able to do that. He was able to produce more clock mechanisms faster than, substantially faster, in fact, that could be produced by hand, and at a much lower cost. He was able eventually, as he continued to improve his productivity and efficiency, he was able to get the cost of the clockwork mechanism down to $10, from $50 to $10, a substantial reduction in cost. The problem he faced was that he had to sell a lot of clocks to make a profit. And what he did is he and two merchants by the name of Porter innovated something new that no one had tried before. That is a marketing technique that is still with us today. They offered a free home trial. They gave the clocks to peddlers who wandered around on the eastern seaboard. They would go into homes, they'd go into farms, they'd go into shops. They would say, "You need a clock." "No, I don't need a clock." "Well, why don't you take it and just try it, keep it for a couple months, see if you like it. I'll come back in a couple months, and then you can either give me the clock back or we can arrange that you could buy the clock." So it's the beginning of the free home trial, and it worked. People who didn't realize they needed clocks got to depend on them, and Eli Terry and his partners sold a great number of clocks. He continued to improve productivity, producing more and more clocks. He then kind of retired. 4 years later, he comes back, and this time he does something that also is very, very crucial. What he has now is he has designed a new clock. It's not an imitation of the old tall clock as his first clock was, but this is an entirely new clock. It's a smaller one. It's going to fit on a shelf or on a mantle. And this clock has been designed specifically thinking about how to produce it with power-driven machinery, specialized power-driven machinery, at an even lower cost than the clocks that his company was producing in the past. These clocks would be easier to produce on machinery. There'd be less filing. They'd be easier to assemble. And by doing this, he was able to get the price of clocks down from $10 to immediately down to $7.50 per clock. By 1810, a handful of workers in a relatively small factory, not even one of the larger ones, but in a relatively small factory, could now produce more clocks in a month than a craftsman could produce in a lifetime. So big expansion of production, tremendous reduction of cost and price, tremendous expansion of the market. Many of the components of a modern factory system were in these early clock factories. They had powered machinery, had a lot of powered machinery, in this case water-powered on the Connecticut River. They began to develop specialized tools to do specialized simple operations. There was also a concomitant division of labor, as workers, instead of doing everything or a number of steps, would begin to concentrate on doing one or two steps. They used templates, patterns, and gauges to make sure that the pieces they produced were within the tolerances, were close enough to the ideal that they could fit the pieces together with a minimum amount of filing. In the 1830s, there were a number of advances in the production of brass. This led to cheaper brass, which again was brought back to be used to make clockworks. Now, brass gears, there was an advantage of making gears and the pieces in the clock out of brass. Brass is a relatively soft metal. You could roll it into relatively thin sheets. And what they did, the new production technology that they used to make brass gears, instead of cutting them out, what they did was they were able to use punch presses to basically stamp out brass gears out of a sheet of brass, the same way you would use a cookie cutter to punch out a pattern of dough on a sheet of dough. By using these punches and presses, they could quickly produce the main parts of the clock, greatly reduce the cost of production. But something else happened here, is that this drive towards uniformity, this drive towards interchangeable parts, was embedded in the design and the production of the machinery itself. That it was the presses, the dies, which is the actual the part of the machine that actually punches out the gear out of the brass. If you were very careful of how you produce the machine itself with hardened metal, what would happen would be is that you would get a great deal of exact measurement from the way the machine came down and punched out the piece itself. In other words, the uniformity that you're looking for, the small tolerances that you're looking for, could be embodied in the machine itself, in the way you design the punch press. You didn't need as many gauges to measure whether or not the part was within the acceptable tolerances or not, whether they would fit together. Much easier than to fit the parts together, faster assembly, lower costs once more. By using large amounts of power-driven machinery, you could produce tremendous numbers of clocks, and because of that, you could bring the price down, and that's exactly what happened. Specialized machinery, faster machinery, less fitting, filing, more division of labor. This process continues all during this period. So that by the 1850s is that the price of a clock had come down to approximately $2 a clock, and before the Civil War, clocks were even being sold for about $1.50. Okay, tremendous reduction in price, creating a mass market for clocks. Now, it is relatively easy to work with wood and to work with brass. It's relatively easy to get the parts to fit together, and the reason is because when you work with these kinds of materials, there are large tolerances. That is, you can tolerate fairly large deviations from the ideal size part. Typically in this period, if that a part came within 1/10 of an inch of the ideal, it would be good enough. You could fit the parts together with a minimum amount of filing and fitting and continue to assemble it and get it out. It was much more difficult, much tougher, to mass produce more complicated products that were made out of iron. The material was harder, more difficult to work with, and because of the kinds of products that were made with iron, the tolerances had to be a great deal smaller. So what was interchangeable parts for clocks would not work for more complicated products made out of iron, steam engines, locomotives, and ultimately the product we're going to discuss that's really going to be at the heart of this discussion, guns. So that the advancement of technique What was necessary was to be able to work iron. Well, the first thing, of course, is you needed the metal. You needed a great deal of this. There's a tremendous increase in demand for iron because more and more things are being produced out of iron. The railroads, locomotives, and the rails became a major source of demand for iron raw material to be used in making the locomotives, the parts of the locomotives, and making the rails. Now, fortunately, during this period when there's this increased demand, there is also an increased supply. In 1828, total pig iron production in the United States was about 130,000 tons. That's a fairly good number. By the beginning of the Civil War in 1859, 1860, is that production of pig iron in the United States, the basic raw material, had risen to approximately 750,000 tons a year. So we're looking at a substantial increase in production of pig iron, the basic material. Well, how do you produce pig iron? It's very simple, really. You build a furnace, looks pretty much like a chimney, except it's a little fatter in the middle. You build it preferably kind of up against a hill, because what you're going to do is you're going to take a fuel. Before 1830, the fuel was always charcoal, slowly roasted wood. You dump the fuel in, that's your fuel, then you dump iron ore on top of it, and you let the heat from the fuel, from the charcoal, heat up the iron ore, burn off the impurities, and what you would get left would be something fairly close to pure iron. You tap the furnace, as they say, the pure iron would run out into sand, and what ran out into the sand in front of the furnace was called pig iron. The reason is the shape, when it ran out, the shape of it reminded the farm boys who were manning the furnaces of pigs. So that was the basic raw material of the Industrial Revolution, pig iron, and there was a tremendous increase in the amount. There was a tremendous increase in the amount because of a number of technological innovations that occurred in the production of pig iron. The most important ones were that really started in 1840. There were experiments before then, but really beginning in 1840, adapting some English technology, two things came together. Anthracite coal, which is large amounts of which were being mined in eastern Pennsylvania, began to replace charcoal as the basic fuel. The big advantage of anthracite coal is that it burns steady, it burns for a long time, it burns hot, and that to produce a given amount of pig iron, you used a lesser amount of anthracite coal. Your fuel savings were about 30% per ton if you use anthracite coal versus charcoal. You also could use it more efficiently. You could actually produce a great deal more pig iron per hour or per worker. Anthracite, again, burns hot. You could do that because of the second innovation that really came in together with anthracite coal, which was, as you all know, if you ever have started a fire and it's not burning very well, what do? Well, you blow on it. You give the fire more oxygen, it burns at a higher heat, and consistently at a higher heat. And if you don't keep blowing on it, it dies back down, and you're back to where you started. So what iron masters always knew is that by blowing air through the iron ore and the fuel, they could get it to burn faster, and they could change the iron ore into iron faster. So there always was a blast of air that would come into the furnace. In the colonial time, in the early 19th century, the blast of air came from a bellows. Very commonly in the early 19th century, the bellows would be driven by a water wheel, which would send cold air into the blast furnace. What they figured out was that if they heated the air, and they could also increase the pressure of the air going into the blast furnace, they could get the furnace to work more efficiently, they could produce more pig iron per hour. And the way you did that was that you substituted a steam engine for a water wheel to get a lot more power to blow the air in, and you used the heat coming out of the furnace, you recycled it in effect to heat up the air going in. This led to tremendous increases in productivity. You could then do two things with pig iron. The first thing you could do is you could take the hot molten pig iron right out of the furnace or reheat it right away and pour it into a mold that would have a pattern of the product you wanted to make. This was called casting iron or cast iron. This was used for a number of important products in colonial America. The largest cast iron product in the first quarter of the century was stoves. They directly would cast the sides, the plates of the stoves. There is a blast furnace just on the other side of Reading, where in fact they still do that. You can go there and they'll show you how the blast furnace works, and then they will pour the hot molten metal into a sand cast, and then they break it open and they show you that this is the side of a cast iron stove. For environmental reasons, they don't use iron anymore. In fact, they cheat a little bit. They use aluminum, but they show you how the process works. The other major use of pig iron was to turn it not into cast iron, but to turn it into wrought iron. And the big difference was the quantity of carbon. Cast iron has a lot of carbon in it. It picks up from the fuel. It's okay for rigidity, for inflexibility, but doesn't have a lot of give. It's brittle. If you want to work the iron into some other kind of shape, you have to get the carbon out of it. You have to turn it into wrought iron. And the way you do that was either you pound it, you basically heat it up, pound it, basically pound the carbon out of it. And that's the main way it was done in the first quarter of the century. Or there was an English method of doing it where basically you heated it up, you stirred it, the carbon kind of left, and then you ran it through a bunch of rollers. You rolled the iron and then into whatever shape you wanted, either as an intermediate product, as a bar. You would then sell it to people like blacksmiths who would take the bar and then start doing the same thing. They would heat it and, of course, turn it into things like horseshoes or whatever shape that was needed. Towards the end of this period, in the really beginning of the 1840s, but this became a major business in the 1850s, the rolling mills who turned the pig iron into wrought iron, the rolling mills some of them began to directly produce rails for the railroads. These were the largest, most technologically advanced iron businesses in the United States. Again, in order to do that, it took a lot of innovation, a lot of new machinery to roll a large piece of iron into rail. And these were the largest, most technologically advanced mills. In fact, many of the innovations in these rail mills were adapted after the Civil War into the production of steel and the production of steel rails. So that there was a lot of the raw material to either that directly became a product or was worked up into an intermediate iron product that became an input into the production of more and more complicated machinery itself, and also the kinds of machines that were produced by power-driven machine tools. Well, the most spectacular one, the most spectacular product of the first half of the 19th century, and I would guess the whole 19th century, was the locomotive. By the 1840s, the standard, what was called the American locomotive, the standard American design was pretty much in place. Didn't change very much for a generation. And the locomotive was a complicated piece of machinery. It had over 5,000 separate parts. Almost all of them were made out of metal, and most of those were made out of iron. Almost every part produced in a locomotive shop was produced on a steam-powered machine tool. So again, this coming together of these different improvements, these different technologies. If you looked into the factories, the factory buildings of the most important locomotive builders, companies like Norris and Baldwin in Philadelphia, the heart of the operation was the machine shops. They would do some of their own casting, they would do some of their own forging, they would buy forged iron ore from mills. But ultimately what would have to happen is these pieces, these big pieces generally, of iron would have to go to the machine shops where they would be machined into these thousands of different parts that were necessary to produce a locomotive. Machine shops didn't just contain powered machine tools, however, they still also contained hand tools. But the heart of them really was these new machines, these steam-powered machines that would cut and shape metal. Products that were made on these machines were not ready to be assembled, to be put together. They almost always had to then be measured to see how off they were from an ideal part. They would have to be hand filed and then compared to a template, compared to a pattern. And when they came within the tolerances, then of course they were ready for final assembly. Assembly was usually done with bolts and rivets. So there was a large number of processes that had to be done in order to make all these various parts that went into a locomotive. It's a very complicated process. The most important power-driven machine in these shops were various types of specialized lathes, machines that were used to cut the metal. They were the most common type of machinery. Norris in the 1850s had about 73 different kinds of lathes out of a total number of power-driven machinery of somewhere around 100. So forming, cutting metal was at the heart of making the parts. These machines already by the 1870s were self-acting. Machinists would, there would be settings on the machine where the machinist would decide how fast the machine had to run, would decide how much of a cut to make on the piece of metal, but would have to load the piece of metal, of course, the piece of iron into the machine. But once the machine started, the machine was hooked up to an overhead shaft with a leather belt, which was connected to a steam engine. Once the machine started, it pretty well was automatic. It was self-acting. This system, of course, was very complicated. There's a lot of different things going on here. This is a very large, complicated manufacturing process. The second thing that went along with this is that it was necessary to keep track of the work, what was in fact happening in the various shops throughout this complex of buildings. So what the large locomotive companies did was that they had to evolve a system of paperwork, what we sometimes call shop orders, to keep track, to control the workflow, to control what was going on. And this system became necessary for them to know how long it was taking to do a certain job and where the bottlenecks were, all the kinds of problems you face when trying to bring a complicated system together. Now, the machinist who designed the machine tools, the machinist who improved the machine tools, the machinist who ran the machine tools, who read the blueprints, many times, in fact, machinists would do the drawing or the sketching of the parts themselves. They were skilled workers. But American machinists were different than English machinists. American machinists had generalized skills. Again, this is another function of the lack of this kind of guild mentality that was rather prevalent still, even in the most advanced machine shops in England. In England, a machinist was trained to basically do one kind of thing, to run one kind of machine, probably producing one kind of part for one kind of product. In America, to some extent, I think because of the lack of skills among machinists, there just weren't enough machinists to go around, is that American machinists tended to have generalized skills. They tended to learn how to use different kinds of machines. They also tended to learn, they had experience, in fact, of using machines like lathes to make different kinds of parts for different products. They didn't spend their whole life making a particular set of parts, say for locomotives or for textile machinery or for clocks for that matter. So machinists in America had transferable skills. They could transfer what they knew from making parts for one kind of product to making parts for other kinds of products. Making parts for different products, especially if new products came along. And this became extremely important in talking about how America industrialized in the 19th century, that these kinds of skills and experience that machinists had could be transferred to new products, to new companies, to new problems. Now, because the locomotive was so large, so complicated, because they were basically produced to order, although there was a standard design, everybody wanted one a little bit different than everybody else, you didn't mass produce locomotives. You literally built them one at a time. But many of the machine shops to build locomotives were some of the most advanced machine shops. And again, this idea of coordinating production, how you go about coordinating production was important. Now, where all of this finally came together, the innovations in building machines, in running machine tools, in organizing work, the place where this came together in the first half of the 19th century was the mass production of guns. Until the early 19th century, guns were made by hand. They were made by gunsmiths, skilled craftsmen. The parts were made by hand, they were hand filed, they were hand fitted. So just like clocks, it took a lot of time and a lot of skill to make a gun. So a gunsmith in England, in America, skilled craftsman, guns cost a lot of money, produced very few guns a year, and this created a number of problems for the major customer of the guns, which were armies. Think about a gun as a machine, as a tool. What's the problem? Okay, you're a general, you're running an army, you're in a war, you got a bunch of guns, you hand them out to all your soldiers. What's your basic problem? Your basic problem is well, how's the gun work? Let's start there before we get to the problem with the guy shooting the gun. A gun is a fairly complicated piece of machinery. Its real problem from a production point of view is that virtually every piece, particularly in the firing mechanism, the lock, hammer comes down, hits the flint, is that virtually every piece is an irregular shape. Not easy to machine. That's why it took so much skill to machine the pieces and get them eventually to fit together. But what does a gun do? Well, you stick a bullet and a powder in the barrel of the gun, some powder in the firing mechanism, flint or something comes down, a matchlock or a flint comes down, and there's a spark, there's an explosion that explodes the powder in the barrel of the gun, and of course that propels the bullet out of the gun at a very high velocity. So we have explosions, we have fire, we have explosions, we have powder exploding, we have bullets charging through the barrel at high speeds. A lot of stuff can go wrong very quickly in a gun. That's the first problem. The second problem is that guns as machines weren't used in factories. They were used out in the field, and usually when you actually began to use the gun, often in fact under very bad environmental circumstances. People carried around guns when it rained, when it snowed, when it was dusty, when there was a lot of dirt around. There's a lot of mud. So it was easy for all these things to get in the gun and follow up the works. Also, the people that carried the guns weren't particularly good about taking care of their guns. And most of them, of course, being farm boys, peasants in Europe, really didn't know much about machinery, and they certainly couldn't fix them if something went wrong. And of course, something went wrong very, very often, particularly at the critical moment when you needed the gun, which was when you were shooting at somebody else and they were shooting at you. If your gun jammed, if it misfired, if it didn't work anymore, and a lot of your soldiers were in that situation, you were at a real disadvantage if the guns from the other army were still firing. That's a good way to lose the battle. It's estimated that in 1812 there were 200,000 rifles in England waiting to be repaired by gunsmiths. They're called armorers in the army. England had a gun crisis, in fact. They didn't have enough guns for their soldiers. Now, and also the armies are getting much larger at the same time, so you need a lot more guns. So what's the answer to that? Well, the answer to that, first really discussed by some in France, the answer to that was a gun that would be easy to repair. Well, how do you do that? Well, the real problem when you're repairing a gun, if a part heats up, explodes, malfunctions, compresses due to stress, whatever happens, is you've got to take the part out or the pieces out. You've got to make a new one, or if you've already made some spare parts, you go to fit it in to replace the malfunctioning part, and what you always find out, it doesn't fit, because every part is handmade. So you have to take it out again, file it down, stick it in again, hope it fits. If it doesn't, you take it out again, file it down some more, fit it in, and then reassemble the gun. It takes a lot of time. Not a lot of people that can do this. You've got a scarce number of skilled gunsmiths who can do this, which slows things down there. And if you're in the middle of a war, this is about the worst possible thing that could happen. So the idea first arose among the French that what if you could produce parts, you could produce copies of the same part that were so much alike to each other, what we would say in technical terms has such small tolerances, small differences, that they were so close together that when you took a broken part out of a gun, you could take any one of the copies of that part, stick it in, and it would fit the first time. In other words, all you had to do was assemble the part. You didn't have to go around, file it down, and try to get it to fit. All you had to do was take it out of a box, jam it in, screw it in, put it back together, and your guys could go off and start shooting at the other guys. Interchangeable parts. The parts are copies of parts, or the same part, are so much alike that you can take one out, put another one in, and have it fit without having to do hand filing, hand grinding. That was the ideal. Well, it didn't get very far in France. There was an attempt to do it. But it got the American ambassador to France very excited about this idea. And the American ambassador to France at the time was Thomas Jefferson. He kept writing back, gee, I just got this great idea over here, we ought to, and this would be great, this is what we ought to do. This really intellectually is an application of kind of the mentality of the Enlightenment, French rationalism, if you like, that kind of stuff. So the idea didn't quite catch on right away, but after a while, in very, very late 1700s, is that the U.S. Army kind of got interested in this idea. Also, in the early 1800s, Jefferson became president. They became much more interested in it when their boss thought it was a good idea. And what the American Army decided to do was a number of things. The first thing they decided to do was to set up an ordnance department, a department that, in fact, would be in charge of producing weaponry. The second thing they decided to do was to set up two government-owned armories, two government-owned gun-producing factories. The first one was set up at a place called Harper's Ferry in what was then Virginia, what is now West Virginia. Why Harper's Ferry? Well, this is about the worst place you could possibly think of setting up an advanced technology factory. It was way in the hell out, nowhere up the Potomac River, in a very rural area. Made absolutely no sense to set it up there. The only reason it was set up there was because George Washington was president, and George Washington was a major land speculator in the area, and thought by establishing the business here, this would help increase land values. Whatever. Later, a second armory was set up in Springfield, Massachusetts, and this made a great deal more sense. Connecticut River Valley. There's a lot of little machine shops. There's a lot of experimentation going on. This is where the clock factories are, up and down the Connecticut River Valley. New England's going to become the industrial center of America in the first half of the 19th century. So the Springfield Armory quickly becomes the dominant armory where experimentation is going to take place. And the Army decides that what we're going to do in these armories is develop a system to mass produce rifles and pistols with interchangeable parts. They also contracted out to private arms producers who also were trying to innovate to produce rifles and pistols with interchangeable parts. The first one, in fact, was Eli Whitney. First one to have a government contract. Like most government contracts, he came in way over budget. He was supposed to produce the rifles in 2 years. It took him 9 years. He claimed he produced rifles with interchangeable parts, but those claims have since been proven false. But for the next 40 years, the goal of the private producers and the armories was to come up with a production system that would mass produce rifles with interchangeable parts. And it was here that most of the important innovations took place that would lead to mass production of complicated products made out of metal. The goal was not to reduce cost, as it was with clocks. In fact, for most of this period, it was more expensive to produce a rifle with machinery than it was to produce it by hand. The reason was because of the very high fixed cost of building and installing the specialized machinery. And again, that's very common in an industrial society. High fixed cost, high upfront cost. And then what you want, of course, are long production runs to spread that fixed cost over a large number of units of output. That didn't work here. And in fact, rifles produced in the armories and by these advanced technological methods for most of this period before the Civil War cost more than rifles produced by hand. But the Army was willing to go along with this because they put a very high value on rifles that would be easy to repair under combat conditions. That obviously was very important to the officers of the U.S. Army. So from early 1800s until really the 1840s, there was this continuous set of innovations in production of rifles. And by the 1820s, by the late 1830s, most of the pieces were in place. More and more specialized machine tools that could cut, that could shape, that could drill irregular pieces of metal. The machine tools got more and more specialized, to be more and more machines. And in fact, one of the most important machines of the 19th century was invented by an Army rifle contractor named Simeon North in order to increase the interchangeability of the parts, reduce the tolerances. This was a milling machine that advanced the shaping of metal to smaller and smaller tolerances. So we have more and more specialized power-driven machinery. We have more and more division of labor. We have, for the first time, a systematic inspection system. Civilian inspectors, Army inspectors, to go around to make sure that, in fact, the parts do conform to the specifications. We have, used by the inspectors, we have a increasingly complicated set of gauges and of measuring devices that are becoming increasingly critical, more exact, to measure the parts. And every part was measured. To measure the part, make sure that it fit the specifications, it came within the tolerances. By the early 1840s, this system had really been perfected, and at a special rifle factory at Harper's Ferry run by a man named John Hall, they were mass producing rifles that came closer than anything had before, came very, very close into producing rifles with interchangeable parts, the 1841 rifle. It took 40 years, but they did it. They were able to produce guns that came very close to being assembled with virtually no fitting. And it is here, this is something we take for granted today, but this was something new, a system set up to mass produce complicated metal products with interchangeable parts, with a minimum amount of fitting and filing. a tremendous innovation. And it wasn't just the specialized machinery, it wasn't just the gauges, it was the system. It was a system to do this efficiently. One of the things they had to do, for example, was to enforce a great deal more factory discipline on the workers. At Harper's Ferry particularly, the workers rebelled against this. They didn't want to have this kind of discipline. They weren't used to it. In fact, they shot one of the superintendents. But it became a modern factory system that could mass produce complicated products. This system was so novel that when, in the 1850s, English engineers came over to take a look at how Americans produced guns, in fact, it was so new to them, despite the fact England has the world's best metal technology, the system was so new to them that, in fact, they called it the American system of production. And the place where all the pieces came together was in the arms manufacturers in Springfield, Massachusetts, in Harper's Ferry, and the private arms manufacturers in the Connecticut River Valley. And what we're going to see as we talk about the second half of the 19th century is how the skills, the ideas, the techniques learned in mass producing guns disseminated throughout, particularly the Atlantic seaboard, and were used then to produce a number of other new products that were coming out that would change the way Americans farmed, would change the way Americans would live, would lead, in fact, to the kind of world that we live in today.